The objective of this video is to learn some strategies in balancing chemical equations. One simple strategy you can use is focusing on the most complex molecule first and balancing the most simplest species, which is the elemental species, later. So what is this most complex one? That means the one with more elements and more atoms. So inspect the given chemical equation and check which one has more elements and more atoms. For example, in this particular one, you can see that C3H8, it has 2 elements. So does most of other molecules you see in the equation. For example, in carbon dioxide, you still see 2 elements. But going into this molecule, C3H8, you can see that you have 3 carbons and 8 hydrogens. So you can consider this one as the most complex molecule. And what is the elemental species? That is oxygen. You can see that oxygen is in a molecular form, but still it's just an element. You have only 2 oxygen atoms attaching to each other. So use the same strategy that you have been using so far. List the elements in both sides and the number of atoms. You have 3 carbons on reactants and you have 1 carbon on product. Hydrogen, you have 8 on reactant, and on products you have only 2 hydrogens. How about oxygens? You have 2 on reactant and you have 2 plus 1. You have 3 oxygen on the product side. Now, since you have 3 carbons on reactant, you're required to have the same number of atoms on products. Remember, we never changed the subscript, only this coefficient. Now, putting this coefficient 3 makes you get 3 multiplied by 1. You're going to get 3 carbons. And then look at the number of hydrogens. You have 8 over here on reactant side. Now, you're required to have 8 on the product side. So what you can do is divide this 8 by 2, you get 4. Troubleshoot. 4 multiplied by 2, you get the same number 8. Now what this does to number of oxygen is 3 multiplied by 2, you get 6 oxygen atoms from carbon dioxide, and 4 multiplied by 1 and 4 oxygen atoms from water. So 6 plus 4, that results in a total of 10 oxygen atoms on the product side. That means you are required to have 10 oxygen atoms on the reactant side as well. Now you have to have 10 oxygen atoms on reactant. Divide this 10 by 2, which will lead you to a 5. Troubleshoot. 5 multiplied by 2, you get 10. Now check if you have all these numbers balanced out on both sides. Now this equation is balanced. So this is balancing by looking at the most complex molecule first and saving the elemental species for later. Right. Another strategy you can use to balance equation is using fractional coefficient for diatomic molecules. Now, in an earlier video, I mentioned that when we balance chemical equation, we go for the simplest whole number ratio, but sometimes it is kind of difficult to get this simplest whole number ratio at once. So one way we can do it is first balance it with fractional coefficient and then find the whole number ratio. So let's list out the elements. You have 2 carbons on reactant, you have 1 carbon on product. Hydrogens, you have 6. Here you have 2. Oxygens, you have 2 oxygen on reactant, and on product side you have 2 plus 1, that is 3 oxygens. Now I'm going to start with the most complex one. we have C2H6. Now I'm going to put 2 over here to make it 2 carbons. That will lead me to 2 carbons, and I have 6 hydrogens over here. So I'm going to turn this number to a 6. I need 6 hydrogens, so I would put the coefficient 3, because if you think about between 2 and 6, you can find number 3 as the coefficient. Troubleshoot 3 multiplied by 2, you get 6. Now you have the number of carbons and hydrogens matched, but how many oxygens do you get? 2 multiplied by 2, you have 4 oxygens coming from carbon dioxide, and 3 multiplied by 1, you get 3 oxygens coming from water. So 4 plus 3, that is a total of 7 oxygen atoms. So that means on the reactant side also you are required to have 7 oxygen atoms. Now if you put this 7 straight over here, that would lead you to a 14. So divide 7 by 2, what do you get? That is 3.5. 3.5 divided by 2 give you 7. Now this is an equation with fractional numbers. Now in a real balanced chemical equation, what we have is the simplest whole number ratio. So we can end up multiplying this whole equation by 2 to get the smallest whole number ratio. Since this 3.5 is a fraction, now we can multiply the whole thing by 2. Now you can rewrite the equation as 2C2H6 plus this 2 multiplied by 3.5, that is 7 oxygens, 2 multiplied by this 2. Remember, you are only multiplying the coefficient. Never touch the subscript. You multiply this factor by this coefficient, that is going to lead to a 4 carbon dioxides plus 2 multiplied by 3, that is 6 water molecules. Now this is your balanced equation. Why? This is the equation that shows you the simplest whole number ratio. Let's look into another type of chemical reaction. Now you can find polyatomic ions in this chemical reaction. And what else do you find? When this reaction takes place, the partners have exchanged each other. For example, on the reactant side, you see nitrate sitting with nickel, but on the product side, you have nitrate sitting with sodium. On the reactant side, you have hydroxide sitting with sodium. On the product side, now the hydroxide is with nickel. So it's like they have exchanged their partners. So in this event, it is quite hard if you try to balance everything element by element. So what we balance is the polyatomic ion as one unit. So what do I mean by that? I'm going to list the components. I have nickel. You see only one nickel atom on reactant side, and then for nitrate, how many nitrate ions do you see? You have 2. So I'm not going to split this nitrate separately as nitrogen and oxygen. Instead, I'm taking nitrate ion as one unit, and I'm going to count how many units I have. I have 2 nitrate units on reactant side. And I'm going to do the same for the product side. I have only one nickel on product side, and how many nitrates I have? I have only one of them. So you don't see that when you have only one, we just don't show it. But you know, when you don't see these brackets, you have only one unit over here. And then sodium. I have only one sodium atom, and this whole hydroxide, it is 1 unit. You don't see it when you have one. You just have one hydroxide, but on this side you have 2 hydroxides and 1 sodium. And the number of nickels on both sides, they are the same. How about the nitrates? You have 2 nitrates on this side, so I'm going to put the coefficient 2. Now 2 multiplied by this 1, you get 2 nitrate units. What else did it do? 2 multiplied, you know there is only 1 sodium. You don't see this subscript. When you don't see the number 1 subscript, you know by default that there is only 1 atom. So 2 multiplied by 1, now you get 2 sodium atoms. If you get 2 sodium atoms on the product side, that means you are required to have 2 sodium atoms on the reactant side. So that means you have to add a coefficient like this. Now adding that coefficient makes you have 2 multiplied by 1, you're going to have 2 hydroxides. Now check if you have everything balanced. You have the nickel atoms balanced and the polyatomic ions, they are balanced as one whole unit, and sodium, they are balanced, hydroxide, they are balanced. Now this equation is balanced.